Okay, so let's continue from where we left. So we have a function and we want to make give sense of an expression of this kind where we have some coefficients and exponential complex exponentials and another um, coefficient in the exponent. We said that the idea is to decompose, for example, periodic functions, and this would be something like this. And as you can see, we have a1 and a minus 1, like so, and all the other terms 0, basically. Cosinus of x is another easy example. Okay, we divide it by 2, and then we have 1 over 2, 1 over 2, and the other 0. Okay, so this is already interesting. We said that some sums and multiplications are all can be all expressed by, of periodic function can be basically all expressed in this kind of series. And the reason why is because we can use multiple times this this kind of expression, basically. Okay, so since this is periodic, you can see that the sum and the product will give periodic behavior as well. It's not a proof, it's just an intuition, but you can start to maybe prove it. Okay, but now, okay, expressing cosinus and sinus in terms of other cosinus and sinus may be interesting, but it's not very, let's say, exotic, if you like, because, okay, there are all oscillations. I'm not saying that it's easy to imagine, but you can if you're careful, you can guess that if you sum many of these waves, you will end up with another wave. It may make sense. Okay. Now I want to push a little bit further, and okay, what I want to remind you of, for example, in the first place, is that, okay, so is this one. So if we remember, the integral of an exponential function is an exponential function, the same way that it goes hand by hand with the derivative of the exponential. It's the same as the derivative, the same function, basically. Okay, so, and this, by the way, also happens when you deal with complex integration, complex numbers. So this x can be a real complex, it doesn't matter. Okay, so let's see if this can help us to, right, so what I want, okay, so let's do another step before jumping into the math. So suppose you have a function, any shape, okay, and then if you remember on the integrations slides, videos, sorry, we can kind of approximate our function with many rectangles. We use the rectangle to approximate the area, that's true, but another way to look at it is that you can kind of chop your function in many horizontal segments, and then you approximate it locally with horizontal small straight lines, okay? The red ones that I'm drawing now. Right, from that you can do many things. You can define your integral as the sum of the rectangles below these red lines, these rectangles here, for example. But another thing that you could do, for example, is to think about your function as a sum of many of these rectangles. Okay? And why I'm saying that? Because, so keep in mind that the integral of an exponential is an exponential, and keep in mind, so and now I want to show you one quick thing. Suppose we we need to do another step before. Sorry about that. So you remember when we talk about integrals, we started from a sum, and then we derived, when we made the sum very small, very refined, with very many steps, we were able to associate these symbols of sum of many countable many, so things you can count with your hands, to an infinite, so a limit procedure again of a function. In this case, the function is approximated by the coefficient. Will become, or let's call it a of x instead of a of an. Let's call it a of x, because we are promoting it to a function, not a list of numbers, so it's continuously varying its value over the line of real numbers. And then e to the x y, for example, and we integrate over dy, and then I need to change this in y, otherwise it's a bit of an issue. Okay, right, minus infinity to infinity. Okay, this is, let's say, the continuous version of the Fourier series. This is the series, and this is called Fourier transform. So the Fourier series, anyway, when you are on a PC or on a laptop where you do calculation, you always end up using the series, because you have finite many bits that you can describe your number out. But in theory, this can be thought as an integral, so span, so a continuous variation of your indexes n, for example. Why I'm saying that? Because suppose now we take the easiest case of the Fourier transform. So what happens when our function a of y is the function 1, is the constant function 1? So let me draw it just now, which is, by the way, a very, actually, I will be more precise. This is 1. Our function is exactly this one, only for a short segment. Okay, so minus 1, and then we do L and minus L. So our function is 1 there in this interval, and it's 0 everywhere else. Okay, it's not a very interesting function. I can see that, but it has a very interesting application, if you like, because if you think about summing many of them and shrinking L to 0, when L goes to 0, basically you can, with these functions, you can approximate any any shape, right? Because these are all the rectangles, and you are sampling your function and making it with many small steps. Okay, so what's the catch here? So the rectangle, this function here, basically says that you have 1 every time, and then is 0 everywhere else outside from L to minus L, meaning that when you go to minus infinity, you can reach at most minus L, because after that is 0, and when you go to infinity, you can reach at most L, because everywhere else is 0. In all this interval here, the function is 1, so we can write 1 if you like, and then we have our e to the x y in dy. Okay, but this is very convenient, because we know what's the integral of this function here, and is exactly e to the I x L minus e to the minus I x L divided by x. Okay, why this x is coming from here? Well, because something, so we need to remember that we are, so this is a bit of a technical issue, which I didn't mention in the integral as a video, but basically, as you can see, this function here is very similar to an exponential like this one. The only difference, if we want to use this this expression, is that also the small interval here must be the same kind. So one thing that we do is we replace this by adding an x here, but since we add an x there, we need to divide by x as well, because otherwise we are cheating. X and x goes here, so they can, if you like, cancel out. And be more specific, this is it's not very neat math, but let me do it this way, which is quicker. And then you can get rid of xy, and you can call it in whatever name you want. It doesn't matter. You will have this this result in the end. Okay, what's nice about this function here is that it's called sinc function. Okay, doesn't matter. It's similar to a sinus, but it's damped, meaning that it oscillates, goes down and up and down and up and down, but every bump decreases in height because there is the x. As you can see, this x is weighting your oscillation. So if you like, is a sinusoid with this function here that on top, that is limiting the height and reducing the height of your sinus. Okay, well, this is nice because we just found a function that allows us to do the Fourier transform of a rectangle. So we have the sinc of x, which is the Fourier transform of e to the I x in dx y, sorry, minus L of L. Okay, now we can then use this to sum all of this component again and basically recreate our function, because basically we are approximating each rectangles with one of these infinite series. So a rectangle, if you like, is an infinite series this weight function here, which is called sinc of x, e to the minus I x y, and this is still y. Keep forgetting that in the y, minus infinity to infinity. Okay, but this is great because basically we see that with this function here, somehow we can approximate every rectangle. And now if we multiply the height, if we change the height of the rectangle, we just multiply this by a number a, and this will be the height of the other number a, and then we can sum many rectangles ai, and then we call them rectangles of x, of L is the size, and xi, and this will give us any function. Okay, almost any function that you can think of. If you play with the I and L, you can do as I showed you up here with these many small rectangles here. Okay, but we decompose it in terms of sinusoids and cosinusoids. Basically, what happened is that if we would plot this sum once you do the transformation, the Fourier transform. By the way, this is exactly what's called the Fourier transform, from going from rectangle to here and from here. So what happens is that you are approximating your rectangle with something of this fashion. So your rectangle has, depending on how many terms you put in your sum, your rectangle is approximated by something that goes like an A rectangle almost, but it still has some oscillatory behavior there. Okay, but that's super nice because this means that we can basically decompose any function with many waves. Okay, and this is super powerful tool that we will exploit many times, and it is used countless many times in physics and math to solve problems. Okay, so you decompose your function in many waves. The difference between the waves is the height and the frequency, so how many oscillations per unit time, basically per unit length, and this is weighted by the y factor, which gives you the frequency, and the sinc will give you the height of your oscillation. Okay, so hope this is helpful. So what I just want to highlight is that we show quickly how to approximate a function in many steps. Okay, like so. Each step can be decomposed with this Fourier transform in many waves, which are these oscillatory terms here with different frequency, and the height is exactly the Fourier transform of the rectangle itself, of the unit rectangle, which is this fancy function sinus sinc, which is called sinc cardinal, which looks like a sinusoid if you start, but then the oscillation is damped and it gets smaller and smaller and smaller around zero. Okay, so this function here is what is related to your rectangle to begin with, and then by adding many of these one, depending how many terms in this sum you can add, supposing you cannot go to infinity, you will end up with something very close to rectangle with some oscillatory behavior you can neglect in many applications. Okay, hope this is interesting, and I will show you some application in differential equations after I've done a video on differential equation next time. Okay, hope you enjoyed. See you next time.